going to be Singh from Multiverse, and the talk is going to be tensor networks with graphical geometry for 5 minutes. Yeah, there you go. This was not uploaded. What? Was not uploaded.
So I'm just going to share it.
He's sharing his screen. Yeah. Yep, that's right. Did you want the clicker or?
No.
No, you're good. Okay.
Okay, so first of all, thanks to the organizers for the opportunity to present here. This talk's going to be slightly different from the flavor of this segment. So this is classical simulation of quantum many-body systems as opposed to quantum. I'll be talking about this work, which we posted on an archive earlier this month. So this is work with Siddhartha Patra and Roman Oros, who are both at the IPC in Spain and also at Multiverse Computing. But many things, so in this work, we generalized a class of numerical algorithms called tensor network algorithms in a certain direction, as I'll explain. But many of the ideas that I'll talk about here were also used in our previous work from last year. So the story for this work was, so last year IBM impressively simulated very deep dynamics of a 2D Ising model on the Eagle processor with 127 qubits. And indeed, so their results showcased a robust and impressive error mitigation scheme, but they also claimed that this will be hard to reproduce with classical simulations. Okay, and it turns out that this is not true. There were several rebuttals, including ours. So we were able to reproduce their results using a tensor network on a laptop and in minutes. And we also went a step further. So we simulated the same dynamics on their larger architectures. So 433 qubits and 1100 qubits just as benchmarks for future experiments. Okay, so the basic setup for this talk is going to be, we're going to have a bunch of spins scattered in space. And we're given a local Hamiltonian. So a local Hamiltonian is a Hamiltonian that's the sum of terms, where each term acts only on a few sites. So by few sites, I mean order 1 in the system size, but here I'm going to assume there are only 2 spins in each term, but these spins could be far away. So they're not necessarily nearest neighbors. Okay, now this is not just a convenient class of Hamiltonians, but it turns out that many, if not most interesting Hamiltonians in quantum many-body physics are local. Think about the Ising model, toric code, and so on and so forth. And our goal is to find the ground state of this Hamiltonian and also simulate dynamics. I'm going to use the context of finding ground states to introduce tensor networks, but as we'll see, the same algorithm can also be used to simulate dynamics. Okay, so we're going to use the class of tensor networks called PEPs, projected entangled pair states. I'll tell you what they are. But I should just mention for completeness that tensor networks can not only be used to simulate spin systems, which is indeed the simplest setting, but they can also be used to simulate bosons, fermions, anyons, and even continuous fields. And they can also go beyond finding ground states. You can find excited states, thermal states, classical partition functions, and so on. Okay, so what I'm going to do next is I'm going to forget about ground states and construct a class of states on the lattice that can be classically simulated. Okay, this is going to be my PEPs class. And then I'll explain what they have to do with ground states. So our building block for constructing this class of states is going to be a Bell state, a maximally entangled state of 2 virtual spins of dimension chi. Okay, so this is my picture for this Bell state. So this picture is actually a picture of a matrix. Okay, so this dot with 2 lines is a matrix with 2 indices. These indices are indices of the matrix, and here it's basically just the identity matrix. Okay, so Bell states are just vectorized identities. Okay, so let's start in one dimension. Okay, so I'm going to arrange a bunch of these Bell states on a line such that 2 virtual spins sit on a single lattice site. Okay, and then I'm going to apply an arbitrary linear map. Okay, so or a gate, generalized gate, need not be unitary. I also call this object a tensor. It's just a linear map from two virtual spins to a d-dimensional vector space where small d is the dimension of my lattice site. So here I've just straightened the same picture, and this is an example of what is called a tensor network. So a bunch of tensors or linear maps that are multiplied together according to some geometry. So there's some language here. So this index here, which gets multiplied between tensors, called a bond index, has a dimension chi. That's the dimension of a Bell state. These indices are called physical indices. So in one dimensions, so this is basically the state that you get on the lattice by this preparation is called a projected entangled pair state. But in 1D, PEPS is also called a matrix product state. Okay. So now you can basically follow the same construction using Bell pairs and applying these linear maps locally to build analogous class of states on, let's say, a two-dimensional square lattice. Here, simply this map's going to be a map from four virtual spins to a d-dimensional vector space. And there's nothing really stopping you from defining this on an arbitrary graph. Okay. So the claim is that this class of states can be efficiently simulated on a classical computer. So what do I mean by simulate here? So I mean two things. So one is it can be efficiently stored in memory. So I need polynomial number of parameters and the number of spins. And second, I can efficiently compute expectation values of local observables, again in polynomial time. Okay, so here, so let's count the number of parameters that are here. So just to quickly show you that this is indeed the case here. So each one of these tensors has chi square times d number of parameters, and there are n of these, one for each side. So the total number of parameters is linear in n. And what I'm not going to explain, but what is also true, is that you can compute expectation values also in a time that grows linearly with system size, but with a larger exponent in this chi. This is also called the bond dimension. And this trend kind of persists for lattice in any dimension. So it's the memory cost and the computational cost is linear in n, but with some exponent of this bond dimension. Okay, and indeed it generalizes to any graph. Okay, so what do these states have to do with ground states? So let me just kind of like briefly mention some formal results in relating these two. So ground states of local Hamiltonians on the one hand and PEPs. So on a 1D lattice, if the Hamiltonian is capped and short-ranged means the spin just talks to nearest neighbor or next to nearest neighbor, then the ground state is a PEPs. Okay, so I put is a in quotes, but what I mean by that is this statement is just a message of a theorem. You can formalize this, and there's really an exact equivalence. So ground states of local gapped Hamiltonians in 1D are matrix product states or 1D PIPs. So in two dimensions, you need a few more adjectives, but there are theorems to kind of staying the same thing. And the other nice thing about PIPs in two dimensions is that they can describe topological order, which is a characteristic of only two-dimensional systems. So in fact, ground states of all your favorite topological models, quantum double models, which includes toroid code, string net models, are an exact PIPs with a small bond dimension. And because of this reason, they have been, both MPS and PIPs in higher dimensions have been used as a theoretical tool to classify gap phases of matter in 1D and 2D. Okay, so that was in theory. So let's say you don't care about theory. You like, I have my favorite Hamiltonian. How do I find the ground state of this Hamiltonian in practice? So in 1D, there are a number of algorithms, black box algorithms. You just throw in your Hamiltonian and you get these tensors out, which correspond to the MPS representation of the ground state. So two popular algorithms are the density matrix normalization group, which I won't talk about much more than this, and just mentioning the name, and then the time evolving block decimation algorithm, TEBD. So I'll say a bit more about this because I'll focus on this algorithm here. So this is nothing other than just simulating imaginary time evolution. So we know that if we take any initial state, any state and evolve it in imaginary time, it will project node of the ground state, provided it's not orthogonal to the ground state. So the idea of this algorithm is start from random value of these tensors, that's some random state inside this class, and then apply this big operator to it, and hopefully it'll project onto the ground state. Now, obviously, this operator is exponentially large, so what you do is you tautorize it into a circuit of two-body gates. And then the basic problem that's addressed by this algorithm is how do you update this state by after applying only one gate. And once you solve that problem, now you can just iterate that and find the ground state. Okay, so pictorially, this is something what you do. So here you apply with a single gate on the MPS and follow some sequence of manipulations, and out comes the final MPS. So I'm not going to talk about how this is done in detail, but what is important to note here is the following, that each update is local. So the MPS gets updated only at the tensors where the gate acts. So all the remaining tensors are left alone. This is one thing. And second thing is, this update does not require or does not depend on the value of all the other tensors. Okay, now this is actually a special property of PEPs only in one dimension. Okay, and then the reason for this is a bit technical, but I'll just say it here for completeness. It's because these tensors can be written in an orthonormal basis on these bonds for the left and right segments of the lattice. So that lets you ignore the rest of the lattice when you're doing these local updates. So in fact, we can rearrange these tensors in some way without obviously changing the state, so that the tensors of this decomposition actually correspond to the Schmidt decomposition of the state. Okay, so the picture is roughly like this. You take any bond, all the tensors to the left of it, you can multiply them and you get the left Schmidt vectors, similarly on the right. And this matrix now actually corresponds to the Schmidt coefficients. So now that we know how to do one gate, we can just apply this many times and then find the ground state. And obviously, it's clear that the same algorithm can be used to also simulate real-time evolution or quantum circuits. Okay, now, so both DMRG and TBD have also been extended to 2 dimensions. So the idea is kind of similar. So here, let's say time evolution of a 2D PEPs. Once again, these are local. The tensor network is updated locally after each gate. But unlike the 1D case, there's no clear relation between these matrices and Schmidt coefficients. Okay? Just for the simple reason that when you cut along a bond, you don't break the state into a left and right half, right? And in 1D, that's a special property only of 1D of a line. So although these gates are local, the impact of this gate is only local. But to do this, you need, so to find these new tensors, you need the remaining tensors. And now here, one makes a sequence of approximations. Or do I consider all the tensors, which is the most accurate case, but also the most expensive? Or do I consider only a few of them, or do I ignore them altogether? And remarkably well, I mean, that kind of works remarkably well for a number of problems. Okay, so let me just mention a few important applications of PEPs as a numerical tool, independent of the formal results. So what have these methods been used for? So MPS or 1D PEPs is absolutely the state of art for simulating 1D lattice systems. It's the go-to method. It's the workhorse of the tensor network community. And it's made a lot of progress in the last 20 years for understanding 1D quantum many-body systems. In 2D, PEPs has also been applied to very challenging models and producing results, for example, comparative with Monte Carlo, for instance. And I'll just mention 2D spin liquids, for example, the Heisenberg model and the Kagome lattice. And then these 2D PEPs can also simulate parallel spin liquids. Okay. Now, so the working intuition is, or the fact that you work with in practice is that a PEPs on any lattice obeys the area law entanglement. So if you suspect that your ground state has an area law entanglement, PEPs is a good case. But on an arbitrary graph, PEPs can accommodate much more entanglement, but as we saw previously, it's going to be harder to simulate because the exponent of the cost of the chi is as large. It's basically the degree of the graph of the PEPs graph. Okay, so most of the successful applications of PEPs, and the ones I've mentioned, and also the ones a lot of people focus on, are for uniform Hamiltonians on lattice geometries, or at most disordered models, but again on lattices. Okay, but we know there are many interesting Hamiltonians that are defined on irregular and densely connected graphs. Here are three examples. Spin glasses. They have rich physics, but they're also relevant for what is called combinatorial optimization. This is a class of classical optimization problems that are also relevant for many problems in the industry. And then quantum chemistry. So here the basic degrees of freedom are actually orbitals, which don't have spatial ordering. And there's a lot of crosstalk because of the underlying long-range electronic interactions. And then even in quantum many-body physics, there are some really interesting models with disordered models with densely connected Hamiltonians, for example, the Sachdev-Kitaev models, which have deep connections also with high-energy physics. Okay, so our goal here somehow is to kind of extend the PEPs, take it from the lattice and apply to these really disordered, densely connected graphs. Okay. Now it turns out, as I've showed, that the PEPs has been, you can define it on a graph in practice, but the cost scales exponentially with the degree of the Hamiltonian, how densely connected the Hamiltonian is. And this obviously becomes expensive for large K. Okay. But this is assuming that the PEPs representation of the ground state has to have the same geometry as the Hamiltonian. I mean, the Hamiltonian comes with the geometry, what spins are talking to what spins. But now we're talking about the ground state, which is one eigenstate of this Hamiltonian. Why should it have the same geometry as the Hamiltonian? So especially given that the geometry of this tensor network is really the geometry of the correlation in the state. So if chi was set to 1, meaning the bond dimension of these tensor networks is 1, you reduce to the case of product states. These are product states. So there is some sense in which you increase chi, you're adding more entanglement into the state. So these are describing states with more and more entanglement. So the geometry of PEPs, these intermediate bonds are carrying correlations between the spins through the network. Okay. So the intuition that the PEPs geometry needs to be the same as the Hamiltonian geometry comes from uniform models. So there we know all the terms in the Hamiltonian are comparable, and so they're equally relevant. So we need to keep we need a PEPs with the same geometry as the Hamiltonian. But for disordered systems, there might be an effectively different correlation geometry at low energies. But the problem is that might be hard to guess. Okay, so the working intuition for us is going to be, we should be able to simulate densely connected disordered Hamiltonians using a sparsely connected PEPs. But how do we choose the geometry of the PEPs? And our proposal is that let's not choose it. Instead, let's allow the geometry of the PEPs to fluctuate during the optimization and adapt dynamically to the structure of the low energy correlations. And how do we do that? So we do that by enforcing that any PEPs tensor can be connected at most to a kappa number of tensors during the optimization. And this kappa is chosen to be much smaller than the degree of the Hamiltonian. And anytime this constraint is violated, we go ahead and delete edges. Okay, so here's roughly the picture. So you might start with the product state, might start applying these gates, which come from which correspond to a densely connected Hamiltonian. And these gates add edges, and at some point you have more than kappa edges. So we kind of introduce some edge deletion strategy here to remove this edge. Okay, so the overall cost of this algorithm is now going to be chi to the kappa, which is much smaller than chi to the k. And what's more is that this edge deletion strategy does not incur additional cost. So how do we choose what edge to delete? So that's really the main decision to be made here. And for that, we kind of assign a score to all the bonds in the network. And then we go ahead and let's say delete the bond with the smallest value of the score. So ideally, the score should measure the impact of the deletion on the state fidelity. So the score we use is this one. So this lambda is the bond matrix that's sitting on all the edges, and we just computed the entropy of that. So this matrix is always it's a singular values of some matrix, so it's always diagonal and positive. So you can define this quantity. Now, like I said, in 1D, this is really the bipartite entanglement entropy of the state. But that's not the case in higher dimensions. So it's really a heuristic. So this is some measure of correlations, but who knows, right? But in the paper, we argue that it is indeed a meaningful heuristic for a number of reasons. So I won't talk about them here. So finally, all that's nice to talk. So how does this do in practice? So we tried two classes of models. So we use this method to find the ground state of classical Ising spin classes with hundreds of spins. And we also applied it to the good old quantum Ising model, translation invariant on a regular lattice. And here the idea was we wanted to assess the impact of these edge deletions while finding the ground state of this model. Okay, so the classical Ising spin glass, maybe you're all familiar, but a quick review. So it's just a bunch of qubits with this Hamiltonian. So there are single side Z terms and two side Z terms, but they can be very densely connected. Okay, so this is a classical Hamiltonian, everything commutes. So all the eigenstates are product states in the Z basis, and we want to find the ground state. It turns out that you can also task the problem of finding the ground state of this Hamiltonian as what is called a quadratic unconstrained binary optimization problem, which is some minimization of a classical function. So here X is just a vector of binary variables and Q is a matrix. And you can use n number of solvers out there to solve this problem, including, for instance, Groby. So we chose some, so we had to choose the value of these couplings here. So we tried two different things. So one is we chose some random values of these couplings, so 8 random spin glasses. And also we chose 9 problems from this open source QPlib database. It's a database of known to be hard problems. So for the random problems, we can set up to 130 spins, but very densely connected, average vertex degree of about 40. QPlib problems, these are not densely connected, but they were large, so up to 1200 spins, and they're also known to be hard. And we compared our flexible PEPS method with this flexible geometry with Groby. We applied 3 methods. The first one is just we simulated quantum annealing. So the idea here is to add a time-dependent transverse field to our spin glass Hamiltonian, such that the initial Hamiltonian is simply the transverse field and the final Hamiltonian is a spin glass Hamiltonian. And then the initial state is just the ground state of the transverse field. So we know from the adiabatic theorem that if I change this transverse field, if I turn it off slowly, then the system will remain close to its ground state and eventually go to the ground state of the final Hamiltonian. So the key point over here is how do you turn this up slowly? So what is the schedule? So we use the exact schedule of the D-wave physical annealer. And this is what we found. So left plot is for randomly generated problems. This is for the structured problems from QPlib. And well, it was mostly bad news. This method actually didn't work so well for us. For random problems especially, we got this large error. And then the reason we traced it down to it's basically just breaking of adiabaticity. And because of accumulation of simulation errors, so there are several sources of errors here: discretized evolution, Trotter error, truncation of singular values. So as a result, the time evolution does not stay close to the annealing trajectory and therefore doesn't converge to the ground state of the final Hamiltonian. So to course correct, we added some imaginary time evolution along the annealing. So you do some real-time evolution, pause, do an imaginary evolution to bring it back to the annealing trajectory, and then so on. And for completion, we also tried purely imaginary time evolution. And we know this projects to the ground state. So this is as described previously. But the interesting thing here is, although the Hamiltonian is classical and the ground state is a product state, imaginary evolution follows through intermediate entangled states. And in fact, the algorithm often converges to entangled state. And in that case, we sampled from the state and returned the product state with the least energy. Let me just quickly show you sample imaginary time evolution of the PEPs with edge deletions. So the algorithm is trying to converge to a product state. You can see most of the edges get deleted. In the end, you're left with an island of entangled state, and then you just basically sample from it. Okay, and this is what we find. Both these methods do better than quantum annealing. So in fact, pure imaginary evolution gave only up to 1% error, whereas hybrid annealing gave up to 4% error. But interestingly, both these methods were better than Groby, which is known to be a very good commercial solver for Kubo problems for some of these problems. So it did beat Groby for some of these problems. And in fact, hybrid annealing, although it overall performs with a larger area, it beat Gurobi more problems. Okay, so the final thing is we wanted to assess the impact of these edge deletions on a uniform model. Okay, so just looked at the 2D transverse field Ising model on a square lattice. And the task was to locate the, so this model has a critical point at some value of the magnetic field, 3.1. So we wanted to kind of locate this and see what happens when you tune this parameter. So this parameter controls whether you have deletions, whether you're deleting edges or not. So the critical point, so we plotted the average value of the magnetization of the ground state as a function of lambda. And here were the expectations that when kappa is 4, so this is a square lattice, each tensor is only connected to 4 neighboring tensors. There are no edge deletions, so you should be able to locate the critical point most accurately. But as I said before, for uniform models, all edges in the Hamiltonian are relevant, and also all edges should be relevant in the PEPs. So when you start deleting edges, this should correspond to, the algorithm should actually find a ground state of a truncated Hamiltonian. So this is a bit subtle, but that was our expectation. And it kind of makes sense if you think about it. So we use this criteria to kind of assess our edge deletion. I mean, if we were really properly deleting edges, properly meaning doing it in a way that has controlled impact on the state, this expectation should be met. And I'll probably running out of time. So I'll just run over this. So here's keeping kappa as 4, no edge deletions. And indeed, we find that this method was able to locate the critical point. But for kappas 2 and 3, we found that obviously it's far away. So you still have these sharp transitions, but clearly not at the critical point of the 2D Ising model. But it was interesting to us that there were still sharp transitions. And we wanted to know what these sharp transitions were. So to do that, we monitored the geometry of the converged PEP. So remember, at any value of lambda, we are using this dynamical geometry PEPs. So where the geometry is changing, but converges to some geometry. So at each value of the lambda, there's a different converged geometry. So we tracked how the geometry changed across these sharp transitions. And we picked the geometry that emerged precisely at these sharp transitions. Okay, now, and then we put an Ising model on that geometry and found its ground state, but using the usual PEPs method without any edge deletion. Okay, so the idea was to confirm that our optimization for the 2D Ising model is actually finding critical points of another model, of a truncated model. And indeed, this is what we found. That here it's actually finding the critical point of a Ising model on a weird graph. And in kappa S2 is actually finding the critical point of the 1D Ising model. So Ising model on a chain. So here kappa S2, each tensor is only connected to its neighbors. So the geometry at the sharp transition is actually just a chain, which just emerged from our optimization. Okay, so the lesson from this exercise was that for uniform models, our edge deletion scheme indeed corresponded to deleting terms from the Hamiltonian. So this kind of gave some kind of an indirect check for our edge deletion. But also kind of highlights some applications of our bond entanglement entropy based truncation. So I haven't shown that plot here, but I can now, instead of the average magnetization, plot the average entropy of the bonds in the network as a function of lambda. And you see that from that plot, this quantity actually locates these critical points. So you can actually use this quantity to locate critical points. And as I've already said, we were trying to optimize, locate the critical point of the 2D Ising model, but on the way, the optimization dynamically traverses critical points in other dimensions. Okay, so that's pretty much it. So we've extended the PEPs algorithm to densely connected disordered models. And so this method can also be used to find ground states of Hamiltonians that are installed on a dynamical lattice. I haven't explained it here, but you can do that. So historically, PEPs was invented to find ground states on a fixed lattice. Then it was generalized to arbitrary but fixed graph. And what we've done is extended this to PEPs with a flexible geometry. Okay, and the geometry was made flexible by introducing a simple edge deletion strategy. Works across a range of benchmarks. In particular, we've shown the potential of this method for solving these hard optimization problems. And final thing is, so in CAPAS2, the flexible PEPS algorithm actually reduces to a flexible MPS algorithm, where the site order is not fixed. So this may be of independent interest. Okay, yeah, thanks.
Thank you.